In this video, we're going to take a look at histograms as a graph for a quantitative variable. So we're going to look at creating and interpreting histograms. So a histogram is a lot like a bar graph, but without any gaps between consecutive bars. Again, it is quantitative data, so typically where one row of our frequency table would end, another one would immediately pick up where that one leaves off. So looking at our histogram here that represents the weights of, I believe there were about 25 huskies from our previous section. Here we have dog weights between 35 to 40, 45 to 40 to 45, 45 to 50, etc. Now, in each of these groups, any dog that is 35 pounds or more, but less than 40 pounds, will get counted in this first rectangle here, which we call a class. Any dog that is 40 pounds or more, but less than 45 pounds, would get counted in this second bar or this second class. So each of these bars in a histogram is called a class, and in this histogram for the dog weights, we have a class width of 5. So we could just take 35 and 40 and find the difference. In the histograms that we're going to look at, all of the classes are going to be of the same width. Although that's not universal, it is the most common to have all of the bars or the classes be the same width. So again, any value that's greater than or equal to 35 but less than 40 goes in our first class. And in our video with the husky dog weights, we did have two huskies that were in between 35 and 40. If the value is greater than or equal to 40 but less than 45, it's going to go into this second class, or it's going to get counted in this second bar, which we had 4 of those, and we can fill out the rest of them as well. Now, here we just use 5 as the class width, which is also, these are called lower class limits here, and we can find that again by taking any two lower class limits and subtracting them. So 40 minus 35 gives us 5. We could also graph a histogram using what's known as a class midpoint. So we just take and add the two values here, 35 and 40, and divide by 2. We get 37.5 as the midpoint of this first class. So here's what a histogram using the class midpoints instead would look like with our 37.5, 42.5, etc., which represents the midpoint of each of these classes. So again, to find the class midpoint, just add the two values and divide by 2, and you can create a histogram using the midpoints. Notice that the difference in midpoints is the same as it was for the class width. 40 minus 35 is 5. 42.5 minus 37.5 is also 5. So again, each of these bars has a class width of 5, even if we're using the midpoints. So we can also make a relative frequency histogram of a data set where the total area of all the rectangles is going to equal 100%. So here we have a different study. So these are not the same huskies that we looked at before, but a new study. And here I have the red lines emphasizing the major values here along each axis, just to make it a little easier to read. Might be able to see faintly these little minor values here. There's 1, 2, 3, 4 of them. So this is this right here is 0.01. This would be 0.005. So each one of these represents a value. Each of these little ones represents a value of 0.05. Now, if we take any rectangle and find its area, so this has a length of 2 and a height of about almost 3.5. If we multiply the length times the height, or the width times the height, we get the area. And if we find the area of all of these big rectangles, it'll add up to 100%, or all of the dogs in the study. So example 1, answer each given the histogram below. So here we have some test scores ranging in the 50s all the way up to in the 90s or 100. And here we have the count, or the frequency, on the vertical axis. So first up, what is the class width? Well, we just take 50 minus, or 60 minus 50, and we end up with a class width of 10. So 60 to 70, 70 to 80 all have a class width of 10. Part B, what is the midpoint of the fourth class? So first, second, third, fourth class is this class right here. And the midpoint, if we take 80 and 90 and add them up and divide by 2, we get 85 as the midpoint, the halfway point between the two ends here of the bar. Part C, what is the relative frequency of the fifth class? So I've included the counts of each of these classes. We want the relative frequency of the fifth class. So we want to know what part of the entire total is the fifth class. So let's see, 1, 2, 3, 4, 5. That's this 11 out of the total. And to find the total, we'll just add up all the heights of all the bars. We have 3, 5, 17, 31, 42. So we have 11 out of 42 as the relative frequency of the fifth class. So, and again, we could find the relative frequency of any class now that we know the total by just putting that height of the bar above 42. All right, example 2, create a histogram from the measurements below. Use a minimum value as the lower class limit of the first class, and then use a class width of 2. So the minimum value in this data set is 1. So we'll start with 1, and then if our class width is 2, we'll have a 1 for our first rectangle on the left, and then adding 2 to that will give us 3, then 5, then 7, then 9, then 11 as our lower class limits. So if we take a look at, here we have greater than or equal to 1 but less than 3, we have 7 of those values. So in this case, greater than or equal to 1 but less than 3 would be a 1 or a 2. So we count 1, 2, 3, 4, 5, 6, 7 of those values in our data set. So we have a 7. This first class has a height of 7 for its frequency. Greater than or equal to 3 but less than 5, or 3 or 4 in our case, we have 5 of those. So there's 1, 2, 3, 4, and 5 for our second class here. And then we get the frequencies for the third, fourth, and fifth class as well. So when making histograms, if you're going to do this by hand, I recommend graph paper because it does make it easier to keep everything organized, and especially with your axes and vertical axes especially. But for the most part, most histograms now are automatically generated by a computer. So, but they do help give us a good idea of what the data looks like in terms of its overall shape, which we'll talk about at the end of this video. All right, example 3, given the histogram below, the weights of 200 dogs, find the total number of dogs whose weight is at least 34 pounds. So at least 34 pounds is going to start at this 34, this lower class limit for this class. So we have 34 to 36, 36 to 38, and 38 to 40. So we have 32. Again, we have 30, 40, and then 1, 2, 3, 4. And then each one of these little tiny tick marks represents a value of 2, frequency of 2. So 30, 32, 34, 36, 38, and 40. We have a 32 here. We have a 14 for the 36 to 38 class. And then we have a 3. It's a little bit more than, it's about halfway between the two here. So we have 3 dogs that weigh between 38 and 40 pounds. So the total number of dogs, which is take 32, 14, and 3 that are at least 34 pounds, is 49. Part B, what percentage of the dogs have weights between 26 and 28 pounds? Well, we had 200 dogs in our study. It told us that in the directions for Part A. So out of those 200 dogs, how many of them have weights between 26 and 28? Well, this one little space above the red line here means 12 out of 200, which is equal to 6%. So 6% of our dogs that we weighed are between 26 and 28 pounds, or greater than or equal to 26, but less than 28. All right, so looking at how histograms can help us in terms of what our data looks like, we have a couple common histogram shapes, which, again, it's important to get an idea of how the data appears and how it's spread out. We have what's known as a uniform distribution, which the bar heights for the histograms are roughly the same. Now, they don't have to be exactly the same, but they do have a pretty much of a level appearance to them if we look at the overall shape. So here we have a uniform distribution where the bars are roughly the same height each. So again, they don't have to be exactly the same height, but they should roughly be about the same height each. We also have where most of our data is in the on the left hand side of the graph, and then it starts to tail as tail off as we go to the right. So we have what's known as right or positively skewed histogram, where the skewness refers to the tail. So here we have a pretty big amount of values that are on the left side of the graph, and then it starts to kind of tail off as we go to the right. So again, skewness refers to where the tail is, and here where tail is towards the right or the positive direction. If you think of the x-axis, going to the right is the positive direction, so that's why it's also known as positively skewed. Again, skewness does refer to the tail, not where the bulk of the data lie, so keep that in mind. We have normal, also known as bell-shaped distribution, where if we kind of trace it out and kind of make it like a curve to get an idea of how this data is, if we trace it out, it makes somewhat like a bell-shaped distribution. You may have heard of bell-shaped curves and bell-shaped distributions before. We're going to spend a lot of time talking about normal distributions in this course. So it is a bit symmetric because the left half and right half are the same, and when we look at it, it does have this bell-shaped appearance to it. So if you think of like an old bell, like in a clock tower or something like that, it resembles that shape. We also have what's known as left or negatively skewed. So we saw where with right, most of the data was on the left side, and then it started to tail as we went to the right. Here, most of our data is on the right, and then it starts to tail as we go to the left. So if we have the bulk of our data on the right side, and then it tails off as we go to the left, that's called left or negatively skewed. Again, the going to the left is towards the negative values if you think of the x-axis. So again, skewness refers to tail. So here we have most of our data tailing off to the left or negatively skewed. We also have what are known as cumulative histograms, where we can look at cumulative frequency or cumulative relative frequency. And here is an example of a cumulative relative frequency which shows a running total of relative frequencies of scores for a mathematics test. So our first values are in the 60s here. We had a low percentage of students get a score here, and then the next one is going to add to the previous one. So for instance, this rectangle here is going to be the cutoff score for this previous rectangle plus this additional height. So it just keeps building up and building up. So we can see the next one here, if we can draw like a horizontal line here, that means that this range of values here for this bar would have been this rectangle above this cutoff line. So with a cumulative frequency or cumulative relative frequency, the bars are either going to get taller or stay level if there's no change. But here with cumulative relative frequency, our final bar is going to be at 100% because now we've counted all the scores for all, in this case, all the test scores that we had available to us. So it just keeps a running total and then builds upon the previous heights before it to create what's known as a cumulative histogram. So, all right, that about does it for this video. Thanks for watching. I'll see you next time.